Normal probability distributions, and this is the lead into inferential statistics. And so inferential statistics is the last portion of the course, but it's the most important one because it actually takes what we've learned in the first two chunks, I guess we could say, and it starts to get us to the point where we can apply it in a meaningful way. All right? So statistics is meant for the purpose of taking information on a smaller scale and using it to project out to a larger scale. All right? So if I can take meaningful representative samples, from a population at large, whatever you define the population to be, doesn't really matter. It's a case-by-case situation. But if you can get a meaningful representative sample and draw conclusions about those samples, then using the techniques that I'm going to teach you, you can project those conclusions out to the population as a whole. All right? And so that's useful information because if you were to choose to do the project, you might say, okay, well, I collected data, and I only got like 100 data points. How does that allow me to draw conclusions about all kindergartners in the tri-state area? Like how does that make sense? These techniques will allow us to make sense out of that. All right, so that's the introductory or the hook. All right, so I've talked about this formula before. It's a nasty formula, really meant to intimidate and scare you, but also it's meant to be appreciated because what this formula does is it creates this curve. All right, this curve is known as a probability density function. Which in statistics we call a PDF, but nobody else uses PDF to represent a probability density function. They use it to represent something else. I'm trying to think of what it stands for. The P stands for portable, D document, I can't remember the F. But it's PDF files, so that's generally what you think of. But you don't think of a curve like this usually. All right. Now, it is generally considered to be a normal distribution if the empirical rule applies. All right. So that's the 68, 95, 99.7 stuff. So that's all the way back to Unit 1. But we're going to get into that in a little bit. All right. So you'll get a little bit of a refresher on that. You're not expected to have remembered it from September. And we're mid-November now. So, yeah, that would be, in my opinion, unrealistic, although some people. So anyway, you look at all the bits and pieces here, you see an E, and E is just a number. Right? It's kind of like pi, where it's a symbol to represent a massive number, well, at least not in terms of size, but in terms of length. It's 2.718, blah, 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 kind of like pi is 3.14159, blah, blah, blah. It's meant to symbolize the blah, blah, blah. So you don't have to write all. E is an actual number. And it's built into your calculator, so you don't actually have to worry about it. The good news is you don't even have to worry really about the E because the normal probability distributions, the standard normal curves, they're all built into your calculators even without using these formulas or any variation of this formula. All right? But you can see, anytime you're dealing with an equation, just thinking back to college algebra, pre-calculus, you took that course, whatever, calculus, an equation needs to have an x and a y in order to be a meaningful equation in two variables. Everything else is going to be some number that you would plug in. So if I have a particular data set, from that data set I'd have a mean and a standard deviation. So that answers the mu, the sigma, here and here. E is a number, pi is a number. So you'd have some algebraic expression that you'd put into your calculator and it would create this curve. The good news is the calculator has functionality for this. All you have to do, if you know the right function in the calculator, all you have to do is tell it what the mean and standard deviation are, and it'll plot that curve for you. All right, so I'll show you how to do that. All right. But this is generally what it's going to look like. Now, the reason why it's called a density function is because it has substance to it. All right, it has an area to it. So all of this stuff gives it density, which we refer to as area. We only call it area because we're in 2 dimensions, x and y. We're not living in 3 dimensions where we have some thickness to it, length, width, and height. It's just x versus y. All right. So all of that substance contained between the curve and the x-axis represent the area, also known as density. So that's why I call it a density function. The reason why this works with probability is because just by the nature of the model, the total area under the curve is equal to 1. Well, the total probability in a distribution is equal to 1. All right. Every point on the curve has a vertical height greater than or equal to 0, and also less than or equal to 1, right, as it turns out. A lot of the curves don't even go as high as 1, so I don't max it out at 1 specifically, but they're non-negative. Can't be negative, just like probability. All right, so what that's telling us is that a curve like this could be a good model for a probability situation. All right, so how does probability fit in all this? If I can draw conclusions about small samples, and then I can determine the probability of a relationship between a sample and a population, that's going to allow me to project from sample to population. All right, this is going to be the key to everything. All right, so all of this stuff here is really just either reviewing what we talked about before, bell-shaped curve that is centered around mu equals 0 or sigma equals 1. That's talking about z-scores from Unit 1, which we're going to review in a few minutes. And that bottom little blurb there is addressing what we were talking about in Unit 1 also. All right, so let's actually look at some particular cases, which is not this. If you wanted to know what the problems were on test number 2, here they were. Huh? Oh, yeah, well, fun. I didn't lie, right? Okay, so I say recall, because that's what people say in math textbooks when you're supposed to remember something. They always say recall for some reason. Recall it instantly, right now. And then I tell you the thing that you're supposed to recall. So about 68% of the data lie within 1 standard deviation of the mean, about 95% within 2. Standard deviation 99.7 within 3. All right. So that corresponds with a probability model. That's telling us that the probabilities for these 3 models would be related to those measures that we have for the empirical rule. It's actually not that these answers are coming from the rule. It's more so that the rule is coming from these answers. All right, from our studies of probability related to that massive function before, and actually the calculus that goes along with it, we're able to come up with these areas. So you got to kind of think of it this way. It was like, historically, a person couldn't take a statistics class until after they completed a course in integral calculus, because they couldn't understand the concepts that led to these numbers. All right. But what people started to realize was that, well, in order to apply statistics, you didn't really have to understand calculus. You just needed the tools. Just like you don't need to know how to build a jackhammer in order to actually use it to bust up some concrete. All right. So that's the idea. So what somebody did was they really dove into the probabilities that would come from all the integral calculus. They made some tables. Then once they made some tables, they built calculators that stored all that information from the tables into the calculators so that folks that did not have any experience in calculus could still make use of this information. And then you could draw the conclusions from that information. All right. So this, unfortunately, is a lot of like hocus pocus. These numbers come from calculus. Just believe me. All right. But yeah, that's a lot of the stuff that we talked about. So this one is probably okay. All right. Anyway, what this is telling me is if I have my standard normal curve, I'll just take the first one. Give it a little too much tail on the right-hand side. And I put a negative one here and a positive one here. What it's telling me is the probability of falling in this interval. All right. So we would be looking at percent of area first, which corresponds to the probability of falling in the interval. Which in Unit 1 you had to memorize. You'll actually never have to memorize these numbers again. I mean, if you did a good job with it, it's already locked in, so yeah, it's there, but it need not be anymore. You can kind of delete those files in your mind and free up some storage space. So let me show you the new and improved. Involves the calculator, so we want to have those out. Hide large display. Yeah, that should actually have enough juice. If it doesn't, let me know. You can use one of mine. No problem. Okay, so I'm looking for the probability that the z-score is between -1 and 1. And just a brief reminder, a z-score, all it is the number of standard deviations that you are away from the mean. I'll talk about that in more detail later on, only because I don't have a particular z-score right now, so we're just really talking in general terms, so it doesn't really make sense to define it. But if I did have a z-score, let's say 5, it would be one group of 5 below the mean and one group of 5 above the mean. Right? But that's not important at the moment. All right, so what I want is the probability of the z-score being between -1 and 1. All right, so what I'm going to do is I'm going to follow a process, which I have right here. It's in a menu that you're familiar with. It's in the second vars menu. The same one that you would use to get the binom stuff. So second vars. So that's the distribution menu. We want normal CDF. All right. We generally don't want normal PDF. I'm not going to ask you any instances in which you would need that. What the normal PDF gives you is the height on the curve. So if I wanted normal PDF, normal PDF, it would be just the height of the curve, so the point on the curve corresponding with a particular z-value. What normal CDF gives you is the area contained between 2 points. So those vertical lines. So this, purple doesn't really stand out. Let me go red. Make it a little bit more, oh, look at that. It's good stuff right there. So this interval here, that's going to give me the normal CDF. So it's going to give me the density. It's going to give me all that area in the middle, or in between 2 vertical lines. So, normal CDF. It asked me for a lower bound. Well, I'm going from -1 to my upper bound of +1. Zero and 1 for your mean and standard deviation, unless they tell you otherwise. Right? If it's a standard normal curve, it's implied that the mean is 0 and the standard deviation is 1. Here, it was actually flat out told to you. You don't have, if you were to put the closed parentheses right after the -1, 1, close them up and hit enter, you'd get the same thing you would get as if you did not put the 0, as if you did put the 0 and 1. All right, so I can actually show you that. So I'd hit enter, right? And then, let's say I just closed them up and did not put these numbers at the end. Same thing, all right? And the reason for that is the calculator knows that if you don't tell it anything, it's because you're working with the standard normal distribution. If you do tell it something, then it knows. It knows. It's obvious because you're saying this is my mean and this is my standard deviation. So that's a clear-cut situation. All right. So this is the decimal form equivalent to the first interval of my empirical rule, about 68%. And that's why we're allowed to use about 68%. Because it was never exactly 68% to begin with. It was always about 68%. So if the percent wasn't exact in and of itself, then we naturally had some wiggle room. So given that wiggle room, it's like, all right, well, if I have some wiggle room, how much is too much? Can I go 1 percentage point? Can I go 2 percentage points? In my experience, and I'm sure other people, but I've studied it, and I've noticed that once you go beyond 2 percentage points, it starts getting sufficiently far away from being normal that your results become sufficiently unreliable. All right, so you get to like 71%, 72%. Your outcomes are less and less reliable to the point where you have to start explaining to people, all right, you got to take this with a grain of salt. You know, like it's not something that you could hang your hat on. It's not something that's completely reliable. It's a good way to get a feel for the data, but you're not going to draw any concrete conclusions. All right, within 2 percentage points, you're satisfied that you have some concrete conclusions that you can draw. All right. So, but that's actually where the 68% comes from. Same idea. If you do it -2 to 2, same calculation, just -2, 2, you get 95% about. I believe it's 0.954-ish. And then 0.997 and a whole bunch of change after that. All right. So that's actually where this stuff comes from. But it's even more than that because it's something called an integral in calculus that determines where these numbers come from. So just for the folks who know a little bit about calculus, what this command does is it tells the calculators to take the antiderivative or the integral of that bt function on the previous page using a lower bound and an upper bound of -1 and 1. So from an a to a b of -1 to 1, using the mean and standard deviation of 0 and 1. So it plugs in those numbers, and then it finds the antiderivative. So this, if you don't have any experience in calc, what this would look like is not going to be overly meaningful for you. But if you do, it's a little bit of a connection that you might find useful, I guess, or at least you could nod your head a little bit. Say, okay, connection. I like it. So it would be this, but specifically swapping out the mean and the standard deviation for 0 and 1. Backwards. It was going to be undefined that way. 0 and 1. And so if you actually run those numbers, you should get these same results. All right, but obviously this is not something even the calculus students would want to do. Right? You're just typing that in. It looks like it would be a nightmare, and it's not overly terrible. It's just there's so much room to make a mistake. So you have a function built into your calculator. Why not use it? All right. So number 1 is very similar to what we just did. So if I needed to find the probability that z is between 0 and 1.5, I would just note it like this. And then we just go right to the final answer, knowing that on your calculator you would be typing in normal CDF 0, 1.5. You use your shortcut menu to do the heavy lifting for you. And again, that's second bars, option 2. At least until they update the calculators again. Mean and standard deviation are 0 and 1. So enter on paste, and you get about 0.433. And ballpark estimates are fine. On a test, if that's something that you would be interested in taking, you would want to follow rounding instructions, but 3 decimals are typically the way to go. My experience is kind of and this is anecdotal, but if you don't know what that word means, that's part of today's lesson, so that's good. It just means generally overly simplistic explanation of is based on my own personal observations, like a 50-50 split between people who are like, project, yes, I'll do that. Paper, oh, anything to not have to take a test. And then the other group is like, oh man, project? Forget that. A test is only going to take me like an hour and a half. I'd rather just do the hour and a half. So it really has broken down that way. When I first offered this, I honestly expected it to be a ghost town in here the day of a test. Everybody's going to do the project. We walked in, almost everybody was here. There was like 4 people who opted for the project. So it's like, okay. So I don't know how it's going to go. And then the other semester, just to justify the 50-50 reference, was the other way around. So greater than -3. So for this one, because it's not a between situation, I'm gonna draw a little diagram here. Just something to get my bearings. Doesn't have to be anything too crazy. But here's -3 roughly, and you don't have to place it precisely, you just need a rough estimate. It's somewhere on the left. Greater than. So that's all values that are to the right of that. So that's all of this stuff here. The reason I do the diagram is to give me a little bit of a sense of what my final answer ought to look like. Because, the first one is pretty cut and dried. It's between 0 and 1.5. I knew what to type in the calculator. Whether it gave me an answer of 0.433 or 0.156, it didn't matter to me. I just knew I typed it in the right way. here I'm a little iffy, but I do know that I should get an answer that's pretty close to 1, because I just shaded in most of the graph. And if the total area under the graph is equal to 1, then, well, I shaded in most of the area, so I shaded in most of 1 unit, so it's got to be like maybe 0.99 something, maybe 0.97 something, 0.93, 0.85 something, but closer to 1 than 0. All right, so how do we pop this into the calculator? Well, let's actually take a look at the calculator. Second var is option 2 again. The lower bound, well, the lower benchmark is -3. The upper bound, well, that could be anything. I want to put infinity in there, but there's no infinity button in my calculator. All right, so what I do is I put in something large. I'll put in 100. All right. Now you might say, how did I know 100? Well, I didn't. Right? I'll show you how we'll solidify a final answer in a second. But I'm going to put in 100 to get started. And I'll just skip that. Nope. There we are. All right, so then I'm going to hit paste and enter, get an answer. I'm just going to pop the answer down. Or I'll just actually leave the answer up here and we'll do it side by side. All right, so second vars, I'm doing it again. Second vars option 2. I'm going to make my large number larger. All right, so you can make it a lot larger or a little larger. It doesn't matter to me. All right, I'm going to make it a little larger, 101. Oh, what the heck was that? Same. That's good. That means regardless of the number that I put in, we're not getting any movement on our probability, which means that I've settled in onto the correct probability. You get an error?
No. When I went too big, it gave me an error.
If you go too big, you get an error. Okay. You put 1,000 and it's the same. Okay.
Did 100 raised to 10 pounds.
Yeah, if you go too large, you get error overflow, right?
When I went to raise the 100 power, it was
Oh, okay. I know that there are some numbers where the calculator will overflow.
Yeah.
That overflow means that you just went too large. So it's like, I'm going to put the biggest number ever in there. And then you're like, okay, that was too big. So maybe I'll put the second biggest number ever. And then that works. All right. But generally, it's going to be okay. So basically, my point is here, if you put 2 different upper bounds, I put 100 and 101. I put in 100, you put in 1,000. You put in like a gazillion. And we got no movement on our final answer. Our decimals were exactly the same. That means that it's not getting any bigger no matter what I put in here, which means that this must be our answer. If you go too small on our upper bound, then there will be some movement, in which case you haven't gone large enough. What the calculator does is it defaults to 1, I think it's E99 for the bounds, but once you change that, it very rarely puts it back. I kind of hesitate to use that as my instructional strategy, just because I find during a test that it's easier to say, just put in some large number, than it is to say, put in 1 E99, because the natural follow-up question is, how do you get that E again? You know, so, and it's kind of annoying, but this is what the calculator would have in there, 1 E99. This is what it would put in, because that's 1 times 10 to the 99th power. So 1 with 99 zeros after it. But what did that do that my 100 didn't? Right? And also, to get that E, let's say you wanted to try to flesh this out on your own. It's this key here, for some reason, labeled EE. I I didn't bother researching this only because I kind of feel like the explanation is going to be so stupid that I'm just going to get annoyed. I feel like all it's going to say is, well, we already had an E right here, so we needed to distinguish this E from that E somehow, so we just threw another E on it, like E for exponent. And it's just going to piss me off if I see that in writing. So I don't want to actually see it. So
Or the E is green, no?
yeah, but you know what? This E is a different E. That's just the letter E. It doesn't do the same thing. So if I kind of force this down your throat, then you're going to have an issue the day of the test. And that issue is, more often than not, you're going to get the wrong answer. Let me just see what the calculator what my calculator thinks E stands. My calculator thinks the number E is 10. Oh, I'm sorry, 0. It says it right in front of me. It usually thinks it's 10, so I was kind of surprised. So let's say I did that, -3, and then I mistakenly selected this E. It looks different, so that's the first red flag. It's nowhere near, and it didn't report an error. That's the worst thing.
I'm getting like error messages all over this thing, no matter which way I try. Whether it's small, large.
Are you using the correct negative?
Yeah, what's the correct
If you get syntax, usually.
Oh, so okay,
So
using that.
go to.
Yeah, and then it just brings me right back.
Right, that's telling you the problem.
All right. Thank you very much. Thanks.
Yeah, if you ever see error syntax, well, actually, not even just syntax, but if you get an error message and it gives you the option to go to, select go to, because more often than not, it'll bring the cursor right to the problem, and then you just got to say what is wrong with this thing that it's telling me is wrong. Yeah, I think it's the same deal.
The minus, yeah.
You want that? You want that?
It does work, yeah.
And that's another kind of head scratching thing on this calculator. Every other calculator is like minus and negative mean the same thing. Why do we need two different keys? We're just going to make the same key. If you were to do it on the computer, like you go to some math website, if you typed in a negative number, you would just use a minus sign. And that would be the end of it. But no, TI has to be difficult. I don't know. I don't know how they cornered the market on this. I mean, I know how they did, but that's just another depressing conversation. So let's move on. To the left of 1.28. So for me, again, that's another diagram. And by the way, just going back to number 2, you look at the number 0.99, roughly 9, 0.999. That's almost 1, and I shaded almost all of the graphs, so there's consistency there. So here's a little weirder, but if this is 0 and this is 1, then 1.28 I'd ballpark it to be about like right here, and I want to go to the left, so that's all this stuff. I don't know if it's going to be like a 0.999 type of situation, but I know that I'm looking at a number that's more than half. Right? I definitely got more than half, maybe more than 0.75. It's just to get my bearings, just to give me a sense of what I'm looking for in terms of a final answer. So second var is option 2. Now to the left means I can go as far as negative infinity. So I'm going to choose some negatively large number. So I'll do my negative 100. I'll go to 1.28. Get rid of that eyesore that was there a second ago. Pop that in. And then do the same thing again. Now, the good thing about, well, one of the good things is that I don't have to go back into the menu to make the quick adjustment. I can just hit second enter or just the up arrow. I like second enter, it's just habit. But if I hit second enter, I could just go back and overwrite, and instead of having the negative 100, make it a negative 101. And I see no change in the value. So I'm pretty comfortable that my answer is going to be, I'll go 4 decimal here just to not overround it. So 0.8997. I'll still snip it in there though, so it's in the notes. Nice.
Way too many men in this class.
Honestly, I didn't know how to respond other than to
Oh. Can I speak out loud for a second?
yes.
So
Take a
we're not
stand.
looking for P of C. So if I put C is approximately 289.899, that's incorrect. Correct? We're looking for P of a number in between a range.
Correct.
So I have to put in the parentheses 0 or whatever the lower less than the higher. Like
Hey, you talk about it in the calculator or on?
on paper, I have to write P parentheses. Example, C less than 0 less than C less than 1.5.
Generally, yes. Generally, yes. Unless the question, I mean, I phrased these questions in such a way that you would have to write the, although I skipped it on that one for some reason. I'll change that in a second. It's a minor adjustment. But on a test, I kind of tend more to cut to the chase. I'll say, what is T of Z less, and you can just work. Yeah, so. It's just less things for me to forget to take off points for later on. It's a win-win for all of us.
So you say round up to the third sig thing. I mean, was the whole number changed there? Would it be 900?
Yeah, so what I was saying is you'll be given rounding instructions on a test. Typically we go three decimals or 3 significant digits. But in this case, I wanted to go 4 because if I went 3, it's going to round it up all the way to a 0.9, and it's going to lose a lot of the texture of the number. So, but yeah, on a test, I would just follow the directions. Because 0 is right in the middle, so regardless of where I place a 1.28, I know it's got to be to the right of 0. And because 0 is a halfway point, that's the 50% mark. So it's got to be more than 0.5. I don't know how much more than 0.5, but I know I'm looking for something more than 0.5. And for me, that's all I need, because the biggest concern that I would ever have is the direction. You know, instead of going, and this is the most common error, instead of going to the left of 1.28, as in negative 100 to 1.28, some folks will start at 1.28 and go to positive 100, going in the wrong direction, and come up with, what would this be, 0.1003. Knowing that your answer should be more than 0.5 will tell you did something wrong. You know, just having a little bit of a sense anyway. All right.
So you want always to answer 100 minus 1.
I do it twice just to make sure that this doesn't change. And then I report it.
Verifying.
Yeah, exactly.
So definitely write the whole thing in.
But definitely write the answer based on whatever the rounding instructions are.
Can you make a joke from my glasses above the car? I don't want to miss anything.
Yeah, sure. But now I'm on the spot, so I gotta think of something.
Maybe some driving.
Oh, driving is always.
Not recorded.
I mean, it's definitely being recorded. Just a question to say. Driving is too easy.
Don't consider it as your lesson.
I mean, do not continue. By no means necessary should you continue speaking about math.
I'm good at writing.
No, but I do think about the hypocrisy. Sometimes that is me, because I do often rail about how, you know, people are terrible drivers, and then I do feel sheepish when I do something stupid, like when I was at the Virginia Road Hillside intersection where you're supposed to yield, but sometimes you just can't fight the impulse where you're like, I think I can make it, but you really can't, but you do it anyway, and then there's the makeup, the moment of like I gotta make up for this travesty that I just committed, and that makeup is you gun it, because it's kind of, like when you jump in front of somebody, you need to justify the fact that you jumped in front of them by not then driving at 22 and a half miles an hour. You know, so, but I also think like, all right, so you're at a traffic light, the guy in front of you is on their phone, and they miss the light turning green, and so they think that because they now gunned it at like 75 miles an hour, that they made up for that mental lapse. But that doesn't do the person who is now stuck at the light any favors. So, yeah, I mean, there definitely is an issue there. I don't know. But I think that's an object for a study, or an idea for a study, is that hanging out at that intersection there, Grasslands, Knollwood, that gas station there, just hang out there, and when the light's red, just look down and see how many people are on their phone. Just the proportion. Let's say first 5 cars. Yeah. And your suspicion could be that more than 60% of the first 5 cars will be on their phone. And then you can collect data over a period of like half an hour or something like that. You know, and I would say don't do it at like noon, because there's no fun in that. You got to do it at 5 p.m. Yeah, when that line is stretched out past the exit to WCC, yeah, that's the fun time.
Professor, have you heard a story about how buying horrible coffee in the morning just ruins your day? Like everything after that just goes.
No, but I'm currently doing an informal study between cold brew coffee and regular coffee, iced coffee, because I read somewhere that the acidity level is much less for cold brew. It's 67% less, and I have some sort of gastrointestinal issue. Not like the disgusting kind that you can't talk about in class, but the painful kind where it just hurts. No, not that one. No, I went to the hospital after this class last week, and I spent 8 hours there. Yeah. White Plains. Oh yeah. Oh, I wish I knew. I would have sent you a remind message. You could have stopped by New York. Yeah, I had no idea. But they were good. They were nice.
Take some of that pink stuff.
No, it was more like we don't know what's wrong with you. Yeah, so now I got to see specialists and everything, but I'm trying to do my part where it's like, all right, well, let's see what I can do on my, like, cut down on acidity, spicy foods, things like that. I know, but I can't cut out coffee completely. Like what kind of person would I be after that? I mean, do I have to inject it directly in my veins? Like, what's the story here? So, but I read that it's 67% less acidity, and it might be placebo effect in action, I guess. But, or maybe, no, that would be Hawthorne. I'll explain all that later. But when you have a perception of what the outcome should be, and because of that perception, that seems to be what is occurring. But I do feel a little bit better after I drink the cold brew than after I drink regular coffee.
You drink it black too, right?
And I drink it black, yeah. Yeah.
It's the best.
Oh, I love it. I mean, I like the flavors. It's nice. I was out in California a couple of years ago before cold brew became popular here, and it introduced me to it, and I was like, this is wonderful. But the caffeine level is just insane. But Dunkin', I think they don't go too crazy with the caffeine, so that's good. The Starbucks will just like, I mean, you'll be.
You got the black eye. That's like 2 shots of espresso.
Yeah, and then yeah. So, but you know what? I saw them making the cold brew, and I'm not getting that anymore at Starbucks.
You know the light roast is.
You know what they do? They take the concentrate, they pour it in the thing, and then they put tap water in it, shake it up, and then give it to you. That's their cold brew. I don't know what they do at Dunkin', They probably do the same thing, but they do it behind the scenes, so I don't have to actually see it. Yeah, yeah, I choose not to. So yeah, that's I'm getting the kit, like the good kit, because yeah, that's how I'm gonna have to go. But I'm researching now.
It's not that hard to do.
No, I've done it a couple times with the Dunkin' blend, but we'll see.
You know what I love doing? You start mixing blends, you know, the vanilla with the hazelnut, then a little of this, you know.
Yeah, but once I start getting the sugary stuff in there, even the sugar-free stuff, it just does something. All right, so we're all back, yeah? Okay. So, percentiles. We haven't really done much with percentiles, but what this will do is give you a z-score when you already know the percentages. All right, so in the previous set of problems, you were given z-scores and you had to come up with the percentages. Now you're given the percentages and you want to come up with the z-score. I think, in all honesty, this is a lot easier because there isn't any funky business with large values involved. So if you have a curve, a normal curve, or something that is reasonably assumed to be normal, that covers 90%, and the 90th percentile would be the z-score, and it's kind of alluded to above, but I wanted to state it explicitly. Z-score separating lower 90% from upper 10%. All right, so what that's telling me is that I got 90% of the data on the low end, some benchmark that's unknown, so this is my 90%. I'll write it as 0.9. And then on the high end, I have the 0.1. And hopefully you could see the benefit of knowing something like this. Anytime you're looking to cut off at a particular percentage point, there is an application for this. We did this with box plots, but we specifically focused on quartiles, 25 percentiles, so 25, 50, 75, 100. Right? But this allows us to do it for any percentile range. Right? So if I wanted to, like as a teacher, I sometimes want to know, the percent of individuals that would fall in a particular category, based on historical data. In terms of a class, if I'm just focusing on a particular class, I don't need to do this. I just count the number of people who got A's, number of people who got B's and C's and so on. Kind of like I did with that conditional probability stuff in the last unit. We just broke it down based on grade. But if I wanted to kind of project out from that information and determine the probability of a person falling into a particular interval, this is something that I could apply. All I would need to know is the mean and standard deviation, right, for the sample. And maybe my benchmark isn't 90, maybe it's 75. Maybe I want to know just passing versus not passing. There's a lot of different things. All right, when they talk about, what is it called, the 1%ers? Yeah. That's the bottom 99% and the top 1%. It's the same idea, it's just using different numbers. All right, so if you have... Yes. Okay, so whatever the percentile is, it has to be on the lower end. And that's the way the function in the calculator understands it, which is good news because that's consistent with the definition. So you don't have to make an adjustment there. All right, so this is the lower percent. So when they say area in the inverse norm function, inv norm, they're saying for that area it's of the lower percent. All right, it's still in the second bars menu. All right, and so what I would do is break out the old calculator, hit second bars, go to option 3, inv norm. The area associated with the lower percent is 0.9. The mean and standard deviation. We're still talking about the standard normal curve. We'll focus on particular cases soon enough, but for now we're just focusing on, again, cases where it's 0 and 1. All right. So go to paste, and you get 1.28. Bless. Twice. So Z is 1.282, I'll go with. All right. Now, legitimate question or concern would be, we're still talking about standard normal curves. What if we're talking about the average number of points scored over a season for a particular team in basketball, or the number of sales at a particular store, right? Or the gross take for over, let's say, the first 10 weeks. 10 weeks seems long. 5 weeks for a new movie. You know, like what about those situations? Those means and standard deviations aren't going to be 0 and 1. What do we do there? That's the next page, right? So, but the second example is pretty much the same deal. It's just 75% is the benchmark. I don't know where it's going to be, but it's going to be more than half of the graph. So the lower bound, or the lower bounded area, would contain 75%. The upper would contain 25%. So that cutoff would represent the line separating the two. So same calculation, just with a 0.75. So second var's option 3, just now 0.75. And so we get that. Say it again? Yeah. Yeah, because that's the third. I should have mentioned that. That's my bad. That's the third quartile.
So this Q2 that'll be 50%.
Correct. All right, that Q3 comes from the box plot. It's the same thing. So Q1, Q3 represents the first and third quartiles. So we get about 0.674 as the z-score. Page 14, 39 and 40.